Okay, are you ready to continue? Yeah, perfect. As you might have noticed, we follow quite closely this book draft that I gave you before. So in order to give a bit of feedback to me, I would like to see how far you followed reading what I was teaching. So last lecture we finished the chapter on Newton type methods for root finding, the general Newton type methods. It was quite fast. So my question is, who has read already chapter 2? Finished reading chapter 2, just to get a bit of an idea. Okay, a few hands go up, but not so many. Who finished reading chapter 1 at least? It's the introduction. Okay, so not so many hands either. So I would really recommend, I mean, it's wonderful that you come here to the lecture, and that's, I think, the main thing that you should do. But in addition, I would really recommend to also look and read for several hours a week. It's not too much, I think, the corresponding chapters, because they say some things a bit more in detail. If you know it already, you can just jump through it quicker. But in particular, the following 2 chapters will be quite fast, because the next 3 even, because they are much more detailed, covered in a course on numerical optimization that is also given in a similar format here, but which you can think of a predecessor course. And what I will repeat here is the basic notions, because we cannot live without the language of optimization in this course, so we need to really rehearse it. It's dense, it's self-contained in this book, but if the next 3 chapters are too dense for you, I would even recommend to revert to either a textbook on numerical optimization or my own script on numerical optimization, which has the same contents, but more spread out. Okay? You can also find that on our teaching page. So this is everything I wanted to say. And please, next time maybe, I hope to see a few more hands for reading the chapters that we already treated. Maybe I should also ask, at least to those that rehearsed or read, are there questions regarding root finding? Just the general setting of root finding? No. Okay, so you're all fine. And then we can now go on and go to the special class of root finding problems, which we find interesting, which is the optimization field. And so we enter chapter 3 on nonlinear optimization. And nonlinear optimization is a generic field. Of course, you can have subclasses of this which are called linear optimization, and we will come to them. But the general way of stating an optimization problem in the form in which we are mostly interested in it is the form that we already had on the blackboard quite sometimes. I just make sure that you are all on board with the notation. The size of the space we just call n. The variables for optimization we call W now, because we want to distinguish them from some other variables appearing in optimization, in optimal control later. And we have an objective function, a scalar function. We have equality constraints. This is a vector valued function. It's a differentiable function, usually twice differentiable. And we have inequalities, and these inequalities we state in the form that they should be smaller than 0. So this is the problem that we want to solve, and we call it 3.1. And the general assumptions are, as I said, scalar function f, of course. G and h can be vector valued. This inequality reads actually component-wise. That means each component of this vector should be smaller than 0. And twice differentiable functions. So that's the setting. And then there are lots of definitions that I could rehearse, but I want to go quickly through that. So what is the task of minimization? It's finding the optimal point in the feasible set. So what is the feasible set? Feasible set is the point of all points that satisfy the inequalities and the equalities and inequalities. So it's a set of all x, call it W in Rn, so that G of W is equal to 0 and H of W is smaller than 0. And then, based on the feasible set, you can define the global optimizer, which is the best minimal point among all points in omega. And you can define also the local minimizer, or a local minimizer. Maybe I should say that both of these expressions just characterize points. So a point can be a global minimizer or a local minimizer. Of course, there can be several of them. So it's usually not unique. Yeah? And sometimes we will sloppily assume that these points are unique, which is the case for many problems of interest. In particular, strictly convex problems have unique minimizers. But just this little bit of language. And there's one definition I want to repeat because I will also use it quite often, and that's the definition of an active constraint. So it's definition 3.4. Notice I jumped over some definitions. An active constraint and an active set is if you have a feasible point, so if you have a omega, w, which is part of this feasible set, then you could check at this point. Of course, the equalities need to be satisfied, but the inequalities can either be strictly satisfied or they can be satisfied with being zero here, right? And those points that actually touch an inequality, so they really are zero, these points we call, these constraints we call active. Yeah? So constraint, we say constraint index I is active at x, at w, if and only if hi of w is equal to 0. It's clear and it's easy, and the visualization of it, and I think it's useful to think of visualizations. You can always think of inequalities of things, or they cut out some part of the whole space. Here's the positive values, here are the negative values of the function h. You could have another one that cuts out another part, and so this could be the space Rn. And these could be two inequalities, and if you are now at this point, then you would not have any active inequality. If you're at this point, then let's say this has the index that could be h2 and this could be h1. Then at this point we have index 2 active, at this point we have index 1 active, and at this we would have 2 active points. And the collection of all at some point, all active indices, is called A of W. And it's of course a subset from all the possible indices, and I give the NH as the number of inequalities here. Okay, so here, for example, this point, if I call it W bar, then A W bar is equal to the set of 1 and 2 at this point. Okay, so that's the active set, and that's the main language I will use. And if there are some words I will use that I didn't define, you are entitled to ask. Okay, please. I want to go into some important special classes, which I mentioned already. So they are special classes of this general form, just so that we know when do we have what. So 3.1, special classes. And the one that I wanted to start with is linear optimization. And maybe I should say that I call it linear optimization here, because it's a linear optimization problem. Historically, it's called linear programming, and that's the case for many of the classes. Linear programming, and so the software and the solvers and the field is very often abbreviated LP. And this problem here, we will very often abbreviate as NLP for nonlinear programming. So programming is just a historical word for optimization. But what is a linear optimization problem? It's just a problem where all these functions f, g, and h are affine, linear plus a constant term. So it would be a problem, maybe I just say it, f, g, h, affine. And of course, that means that for the objective f of w, you could just choose the linear part, because the constant will not change the solution, so you usually omit the constant, and for g of w you will choose, for example, a W minus B, A being a matrix of suitable dimensions, and then the same for H. So we could call this matrix CW minus D. And then we have a so-called linear program. It's a special case, and it's something that you can solve with special software. So once you have that, please notice. In the environment that we use in this Casati environment, I should say that we will generally always formulate these functions because it's much more convenient than specifying the matrices here. And then it will generate for you these internal matrices automatically, so you don't need to care about generating them. So quadratic optimization is a slight extension of this, or QP is the abbreviation, as before, for programming. And here the only change is in the objective. So the constraints are still affine as before, but f of w is given by a quadratic function, and this quadratic function we could state like this: C transpose w plus a quadratic term which is w transpose b w. This b is a symmetric matrix of the same dimension as w, of course, squared. And this matrix decides actually about an important property of this problem, namely if it's convex or not. So there exist QPs which are convex, and there exist QPs which are not convex. We will discuss convexity in a minute. But maybe I should already state that this matrix B is called the Hessian matrix. Why is it called the Hessian matrix? Because it is the second derivative of the objective. At any point, it's a constant second derivative, so it doesn't matter which w I use to evaluate it, it's the same second derivative everywhere. And this matrix decides on convexity or not. But I will outline convexity in a minute. And maybe one thing I should point out is that if this matrix B is 0, you would just have an LP. So you see immediately that NLP is the superclass, QP is a subclass of it, and LP is a subclass of that, right? It's getting simpler and simpler. Linear programming is, so to say, one of the simplest classes. There is maybe a little remark. Sometimes people wonder why this B is symmetric. So I assume actually B being symmetric. It's something that is quite easy to see why we choose B always symmetric. If we wouldn't choose B to be symmetric, you could still compute its second derivative, and that would be a symmetric matrix. I mean, second derivatives will be symmetric because this operation where you multiply it from left and right with a W actually makes the non-symmetric part of the matrix B anyway not survive. So it's only the symmetric part of the matrix B that will matter, and therefore you can directly assume it to be symmetric. Yes?
Doesn't it also follow from that f of w
yes.
is like 2 times derivable?
Yes, exactly.
Does it also
so
result from Schwarz's?
Yes, anyway, maybe just I should say any function which is twice differentiable, twice continuously differentiable has a symmetric Hessian matrix, right? And this symmetric matrix is, if you choose this thing to be symmetric, is identical to B. And if this would not be symmetric, then you could compute the Hessian matrix, and this is a side remark, so maybe I just put it somewhere very small here. The side remark is that otherwise the second derivative, or if you do it by not assuming symmetry here, then you would get just B plus B transpose half, which is the symmetric part of B. So that would be the correct way to differentiate it for any matrix B, but because it's anyway the symmetric part that survives, we will directly assume it to be symmetric, and that's it. So there is no information that a non-symmetric matrix could bring into your QP, and therefore it's the most general form of a quadratic objective function that you can have. As I said, the constant term could be omitted because it doesn't change the result of optimization. I said that this matrix decides on convexity, but I didn't say what convexity is, so let me define briefly what convex optimization is. It's one of the main dividing lines in the field. So what are convex optimization problems? Convex optimization problems are problems where f is a convex function on the set omega, which is also a convex set. So omega convex f restricted to omega maybe to be the most general convex, then this is a convex optimization problem. Okay. So if you have a problem stated in the form above and you can somehow check that your set omega is a convex set and your function f on this set is a convex function, then 3.1 is a convex optimization problem. So I could now define what is convexity. Who is familiar with the concept of a convex function? So do you know what is a convex function? Who does know what is a convex function? And who does not know what is a convex function? Please be honest. Okay. Not so many people. And it in mathematical terms, I will just decide to state it and draw it quickly. So a set omega is convex if you take 2 points out of the set and you connect them and the whole line is contained in that set. So that's quite intuitive. It's also what we usually use in daily life when we talk about convex lenses, for example, in optics or other convex bodies, convex surfaces. What is then for a function, a short definition would be a function f is convex if its epigraph is a convex set. So that would be one way. The other way to state it is that if you have here w and here f of w, that your function, when you draw it, and you take 2 points out of the epigraph, so this could be these 2 points, then they should be above they should be still contained in the epigraph. That means they should be above the point, and of course it's most restrictive when you check it for the boundary points. So very often people define convexity as being if you take 2 points and you evaluate your function on a linear combination of these 2 points, then the function value should be below the corresponding value on the secant of this function. So these would be the two definitions of convex sets and convex functions, which I will not deeply recover here. But there's one theorem which makes convexity so interesting and which you can also very easily prove actually. The theorem says, it's called theorem 3.10. Local implies global optimality for convex problems. And that means if you have a local minimizer of a convex optimization, local optimality implies global optimality. That means if you have found a local minimizer of a convex optimization problem, there is the guarantee that you will have a global optimizer. And intuitively, it's relatively easy to see that. I will just make a figure. So if you have something where you want to visualize 2 local minima, you would usually draw such a thing, and you will directly see that there is that this is not a convex function. You could actually draw this line between the 2 local minima and you would have some deeper points here. And you immediately see that if you would actually have a convex function, that could be, for example, the convexification of your function, you would only end up with one global minimum, because the bad local minima would be destroyed by the convexification, because they will have lines going down. It's not a proof, it's just a bit of an argument. The proof is also relatively easy, but I don't want to dig into it if there's no question on it. So that's basic facts that can be useful to know. So when you have a local minimum of a convex problem, you're done, you know everything. That is, of course, it looks trivial for one-dimensional problems, right? But for 10,000 dimensional problems, which you also might have, it really is a wonderful thing, because you can check convexity by checking a few things. For example, linear functions are convex, so an LP is by definition always convex, and then you can directly conclude you can find a local minimum, and that's the global one. So it's a wonderful fact. I will very often use a symbol, so that's definition 3.11. That is customary in the field of optimization, and which is sometimes even used to define optimization problems, but that's not what I will usually do. But a symmetric matrix B that is equal to B transpose is positive semi-definite. So that's a statement. If and only if all the eigenvalues of this matrix, I call it maybe this, eigenvalues bigger than 0, that's MATLAB way of writing. Yeah? And we will usually, this is not correct mathematics, so I should put it into this form. But that's, and this is now the correct way how I will state it, is I say B is bigger than 0 in this matrix sense. This is a matrix inequality where I use a curly bigger than, which just has the meaning that a matrix should have positive eigenvalues only. This can be generalized. You can easily say such things like A is a bigger matrix. I mean, two symmetric matrices can be compared with this inequality, with this generalized inequality, by just defining A minus B to be positive definite. And one can show that this really defines a half order on the space of symmetric matrices. Okay, so that's just language. And we will actually also include a stricter notion, namely positive definite. And that is when all eigenvalues are strictly bigger than 0, and that we will denote by B strictly bigger than 0. So there's only one curly B. And that's the two statements which I will very often use in this lecture to say something about the eigenvalues of a matrix, a symmetric matrix, in order to save words and also to make it better and more compact. So now there is one thing that is very useful about convex functions, and there are a few things that I want you to know, namely two theorems. Theorem 3.12 is the one that I think is most often used in order to prove convexity of functions. I mean, it's one of the possibilities, but if you have a function which is twice differentiable, then actually its Hessian matrix must be a positive semi-definite matrix, if and only if. Yeah? So F element in C2 of some, of course the dimensions are from Rn to R. From Rn to R. So then F is convex as a function if and only if the second derivative of F at any point W is a positive semi-definite matrix for all W. And maybe I should, I think this is okay, but it's of course not the most general form. So you could also restrict it to a convex set. So you could also define the function only for example, for positive numbers or such things. And then it would be defined on a convex feasible set, and you check this only on the convex feasible set. So maybe do you want an example for this little thing? No. Okay, it's clear. It's optically, it's clear. Convexity means positive curvature. In the one-dimensional case, it's really positive curvature. 2 dimensions, it's something which has this beautiful shape of a valley. And in higher dimensions, it's difficult to imagine, but it's all expressed by the eigenvalues being positive. There's another useful fact which I just jumped over, but I want to still keep it because it's also useful. So it's theorem 3.8. And that is something that is very practical and easy to use to check convexity of sets. Because very often, and also here, we define sets by inequalities. And so we see here h should be smaller than 0. That's a statement that defines a feasible set. So the question would now be, if you see some functions h, you look at it, could you see and say this is actually a convex problem or not a convex problem? And there is an easy way to say something of this form, namely, we know that sublevel sets of convex functions are convex sets. So what is a sublevel set? Maybe first I should give you the picture. The picture is that you have a function, maybe this would be a two-dimensional convex function. Yeah? At some point, I mean, this is like the height of this f, w, and do I call it f here? I call it h, and I do it also here. And here would be the space Rn. A sublevel set would now be the set of all points where this function is below 0. So let's just assume 0 is maybe, this was a bad plot. I put this origin a bit higher. So then 0 would be here. And you could see that the intersection of this with the plane 0 is here. And so this would be the sublevel set. It's just a circle. You could think of if you have a valley and you put water into it, then the water surface is, so to say, the set of the sublevel set. And so a sublevel set of a convex function is convex. Convex h from Rn to R convex. And that's very useful in order to see directly that something is convex set. So maybe I should also be sure that we have the language right. A function f is concave. You call a function concave if and only if minus f is a convex function. So that's the definition for convex functions. Concave functions, sometimes it's useful to talk about concave functions. I mean, a concave function looks like this. It's easy. What is maybe less intuitive, or I should really point it out, there is no concave set. Yeah? So a set, concavity is something that a function can have, and sets are convex or not convex. Yeah? A function can be convex, it can be concave, that's also as nice as convex, it's just the other direction. And then it can be nothing of the two. It can also be both. Yeah? And that's actually an interesting thing. If a function is both convex and both concave, then the function is affine. Yeah? That's clear. Yeah? So I don't need to write it down. I mean, it's clear. So it's positively curved, it's negatively curved, but it includes zero curvature, so it must have zero curvature. Maybe I should also say that implicitly this implies that if you have a sublevel set of a convex function and you intersect it with the sublevel set of the negative of this function, then it's actually the equality constraint. But it's only giving convex sets if both the function itself and the negative of the function are convex, which means that it must be an affine function. And so what we know is that the feasible set, and this is something I should definitely state, but I think I don't have a... I think I have it as a remark. And what I want to say is that omega is convex. It's a convex set if, I mean, that's a sufficient, it's a sufficient condition. If G is affine, so it has this form that we stated above for the LP, and all HI are convex. Yeah, so each single component of the vector H must be a convex function, and each single component of G must be an affine function. That's it. And of course, if also the F is convex, then we have a convex optimization problem. So we can very easily look at such a function F, G, and H, look at them. If we know about their convexity properties, we can actually say this is a convex optimization problem by just looking at them, as long as we are able to detect convexity of functions, which we can do by either this little theorem, but there are many other ways to check convexity of functions. And most often we check convexity of functions by some concatenation rules, which are similar to how do you check differentiability of functions. I mean, if you have a differentiable function, you plug it into another differentiable function, you add a differentiable function to it, you get another differentiable function, and you don't need to actually each time verify the differentiability by actually proving some limits, right? And the same holds for convexity. So there's a way of automatically finding out if a function, which consists of several calls of other functions, if that is a convex function or not. Actually, or not is not true. You can easily verify that a function is convex, and the decision that your function is not convex is a bit more involved, because there could be some operations that somehow together make it convex, even though each single operation would destroy convexity. So that's just general remarks, and I should say that there are some software tools, YALMIP or CVX, for example, which actually detect convexity of your expressions that you state, and that can be quite useful and interesting. So now I want to ask a question, and this is a simple one. So if you have a function fw equals c transpose w plus 1/2 w transpose bw, when is this function convex? Of course, it's a simple exercise. Yeah?
When the t is positive definite.
Exactly. So it's convex if and only if b is positive definite, and that's it. And therefore, we can directly conclude, if I look at my overview, linear optimization problems, okay, they have only affine functions. F is convex, an affine function is convex. G is affine, H is affine, and therefore also convex. And so a linear program or linear optimization problem is always convex. And for a QP, it's slightly more involved. So a QP is convex if and only if the matrix B is positive definite, semi-definite. Okay, so simple and clean. What I should say is that if you ask a quadratic programming solver, so an optimization routine that solves QPs, you will pass to this solver matrix B. This solver might either be a convex QP solver, then it would miserably fail if this matrix is not positive definite, or it will be a generic QP solver, which very rarely exists actually. But this solver can actually handle sometimes indefinite or even negative definite Hessian matrices. But it will definitely, and most probably, if this solver gives you answers in short timescales, it will not give you the global minimum, but maybe a local minimum to your QP. Yeah? So the nice QPs are the ones with the convex ones. Some solvers actually even fail when they don't get it. Some other solvers might still deliver you some local minimum of the QP, but it's not, you should know that it's not the global one then. Yeah? So global QP solving is as difficult as other global optimization. Okay. Are there questions regarding this classification and the big dividing lines or most important classes I wanted to share with you? Okay. If it's not the case, I would like to directly go on and state a few conditions which help us to specify when we have a local minimum. And actually, they are, in the case of convex problems, even telling us that we have a global one. So that's why they are quite exciting in some contexts. So let me just say we talk about first order optimality conditions. And it gets tough. So this could be derived, and it takes several hours of lectures to derive it decently. But I want to directly present you the result of a large body of research, which is very useful and widely used. So you don't need to know how to derive it. But there is some theorem which I directly want to start with, and that's the main theorem, 3.14, and it's called the Karush-Kuhn-Tucker conditions. And abbreviated KKT. It was derived, I think, in 1934 by Karush and by Kuhn and Tucker in the 50s in PhD theses in the United States. And they actually looked at the general NLP that we have at the top there, and they specified necessary conditions for optimality. And so the theorem says if you have a local minimizer, so if W star is a local minimizer of 3.1 of our problem, and a technical condition holds, and I will specify it in a minute, and LICQ, it's an abbreviation, holds at W star, then some things must exist, namely so-called Lagrange multipliers, and then with these multipliers some conditions should be satisfied. And so I will just say then there exist lambda and mu, the dimensions I will not specify here, they are of the constraints, equalities and inequality dimensions. And I give them already a star, I think, such that, and now comes the interesting things, the gradient of your objective and the gradients of your constraints, each weighted with these multipliers, should add to 0. So there exists some multipliers so that they add to 0. And this is the most exciting condition. It's very non-trivial, of course, if you just see it for the first time. I will discuss the notation in a minute, but let me first state all of these conditions. So then, of course, if it's a local minimizer, it must be a feasible point. So it should satisfy the equalities. It should also satisfy the inequalities. So that's straightforward. And then it should also satisfy some extra conditions which are related to these multipliers mu. So these multipliers mu should be positive, each component of them. And the product of mu and h, which I could write like this, mu star transpose times h of W star, should be equal to 0. I can also directly make it component-wise, because each of these components must be 0 if all these have the same sign and all these have the same sign. The product will anyway be a negative number, right? So, and if it's 0, then each component must be 0. So this is one way to write it, and I think I prefer even to put an index here, because that holds index-wise and this holds index-wise, and then I can directly say I from 1 to nh. Yeah, so this is the complete statement of the Karush-Kuhn-Tucker conditions. We could give them the equation numbers, but I don't. And now I need to specify a few things that I used here in this definition. And the most important is, I think, LICQ. So what is LICQ? Before I can even understand this theorem, I need to understand what is LICQ. So LICQ is linear independence constraint qualification. LICQ. And it's defined only for feasible points at any W in the feasible set. we say LICQ holds if and only if, and now I should define it, the gradients of all the equalities at this point, maybe I say G1 up to GNG, so all these gradients are linearly independent, but not only they, but also we also add the indices of the constraints, the inequality constraints, but only for I element in the active set at this point. So that is quite, I mean, it's a restriction. Only those that are active count, and those that are not active, they don't matter for LICQ. So are linearly independent. And linearly independent means they span a space in a subspace of Rn, which has the same dimension as the number of vectors that we have here. There's another way to write it. I mean, you see here already the numbering is a bit cumbersome. I say here 1 to ng, that's clear, right? But here it just says those indices from A, and then you collect all these vectors together, and this forms a linearly independent set of constraints. And there's one other way, and that sometimes is a useful thing. You can define a function g tilde of w at some point, at such a point that is in the feasible set, and I define it to be the function that is the concatenation of my equalities, and then it comes only those components that are active. So here I have hi of w for I element in the active set. So of course this is a function that is a bit hypothetical, because at every different point it could have different components that would change dimensions. But if I fix the set, the active set, I could define such a function, g tilde, and even assume that it's a well-defined function. So at some point, and now I could compute the derivative of this function, g tilde, with respect to w, at this point w, and I will get all the gradients transposed here, g w transpose, and then I will get here all the gradients from the hi, and you see that this matrix is actually telling you everything about LICQ. So this matrix I could say should have full rank. So this dg tilde dw has full rank is the same as saying LICQ holds. Okay? So relatively quick. And these Karush-Kuntaka conditions hold for any NLP, and they only say something about a local minimizer. So they are something that necessarily holds at every local minimizer, and so we call them first order necessary conditions for optimality, and we abbreviate that as FONC. So if you want to have short for KKT conditions, I call it FONC, FONC, okay? Just so that we know what we mean. And what I said already in words, but which I want to specify as a decent theorem, is that for convex problems, it's actually much stronger. These are just necessary conditions for a general NLP, but for a convex problem, they would be, of course, necessary, but they would also be sufficient. So there is theorem 3.15 that says if this point 3.1 is a convex problem, right? And W and at W star holds LICQ. That's of course a technical restriction which is a bit nasty. There could be other constraint qualifications. Then there is an identity or a full equivalence between W star being a global minimizer and the KKT conditions. So if you have a convex problem, it's actually enough to find these. So there exist lambda and mu star so that KKT, these KKT conditions hold. Maybe I should be very accurate and say, when I say KKT conditions, then I usually mean this set of equations. Yeah. So, this was quite intense, I think. So what I propose now is to have a short break, but after the break I have two options. One is I really discuss in few details, which we also do in the book, the meaning of Lagrange multipliers from an application perspective. So how can we imagine what they mean? We will not prove it. That's not the main aim here. So we can talk a bit about the meaning of them, if that's desired, and I will ask in the break what is the desire. Yeah? And in any case, we will start at 3:15. We will continue with the lecture. Okay? Good. So I would like to continue. And based on a bit of feedback, I think I will slightly illustrate what we just said before. After introducing a few more definitions, just to be sure that we have the language right. And the two definitions that I still want to share with you, which are related to the KKT conditions, is first the concept of the Lagrangian function. That's something that you have heard about, surely, but that I want to define. A Lagrangian function in optimization is a function that we call typically L, some variant of L. It's a function that depends on W, the primal variables, and on the multipliers lambda and mu, which sometimes are called the dual variables. And it is just a mix of everything. Namely, it's f of W plus lambda transpose G of W. Yeah? So it's actually a linear combination of all the constraints. And the same for the inequalities. So here we have the multipliers mu of T times H of W. That's the definition of the Lagrangian function. And this definition, you could just say, is a shorthand for writing the KKT conditions faster. Namely, the first KKT condition now reads just there exists multipliers such that the gradient of the Lagrangian function with respect to the primal variables at the point W star, lambda star, and mu star is 0. So you could think from the first perspective, the introduction of the Lagrangian function is just a way to make the KKT conditions easier to write down. The first KKT condition, that was the sum of all these gradients, each weighted by the corresponding multiplier, and you can obtain the same sum by computing the gradient of this Lagrangian function with respect to the variable W. I would like to make a few remarks also just to be sure that we are all on the same page. The first one is a very straightforward one. If you have no inequalities, so that means you have a problem where there is no function h, which just isn't there, then of course your Lagrangian will just depend on W and lambda. And the KKT conditions simplify to a very short expression, namely you just say there must be something like a point which makes the gradient of the Lagrangian 0 for W star and lambda star, and also the equality constraints should be equal to 0. And that's it, because there's no multipliers. These would be the KKT conditions for inequality constraints. For equality constraint optimization. So in that case, they would be particularly simple. And please note one thing that will be important for Newton type optimization. So these conditions, how many conditions are they? It's the dimension of W plus the dimension of G. And how many unknowns you could have in the system? It's the dimension of W plus the dimension of lambda. The dimension of lambda is the same as for G. So this is a square nonlinear system of equations, which means it defines a root finding problem in a nice form. And very often, many algorithms will actually, for equality constraint optimization, just try to solve this with one of the Newton type methods we defined before. So that's a little remark. Outlook to the next chapter. The second remark is that in these KKT conditions, that I didn't restate here on this blackboard, but there was this condition that the multipliers mu I should be bigger than 0. Right? It sounds quite arbitrary. Why should they be bigger than 0? And that is something that can be motivated in many different ways. And it's, I think, best to motivate it from a physical perspective. So in some sense, and that is the intuition that I want to give you, the constraints, you could think of the constraints as some fences or whatever that push against an object that wants to roll down a hill. Yeah, so if you have a landscape for an optimization landscape, you could think of it being a landscape here in the Black Forest. You have a ball, that's the point that you regard as the minimizer, and the ball will roll down to the minimum point, of course. But if there's a fence, the ball will stop. And the fence will, in optimization at least, it will have a forbidden side, and that's, so to say, the property of your neighbor. You are not allowed to go there, and it will have an allowed side. And on the allowed side, you will be pushed into your domain by the force. And otherwise, a fence that is, so to say, on the upper side of your territory, and you roll the ball there, it will not hold the ball. Yeah, so that would be a fence which would exert a force with the negative sign. That doesn't happen. Actually, the fence will only exert a positive sign if you push against it. Yeah? So this is, so to say, related to the fact that inequalities can only push and not pull. This is, of course, not can only push, not pull. So that's, so to say, a bit of an intuition behind it. The other point that is maybe aesthetic and maybe interesting for you to note is that if you have a convex optimization problem which is convex in the strictest sense, namely the function f is convex and all the functions h are convex and g are affine, then if the multipliers mu are positive, which they should be, then these are positively weighted convex functions. And a positively weighted convex function, if you add it to another convex function, it will remain a convex function. So there is just a convex function. This is affine, so it's also convex. And this is a sum of convex functions. So the Lagrangian is also convex if this condition holds, if you had a convex problem. So that somehow is a nice property. It's not a proof why they should be positive, of course, but it's just something I wanted to point out. So the Lagrangian function for convex problem functions is convex in W if all the multipliers are positive. That makes it easy and useful to discuss such concepts as weak and strong duality, which is not the subject of this course. There's another point, and if you regard the KKT conditions that we just had, I just said there's this first thing that says the inequality should be negative, the multipliers should be positive, and the product of the two, mu I, and I make a star here, to make sure that this is at the optimal point, that the product should be 0. And these conditions together we call complementarity conditions. And these complementarity conditions you could visualize as defining a set. That's quite interesting if you look at it in the space of two axes. Namely, one axis could be the constraint hi of W. The other axis could be the mu I. And now what do these conditions say? They say that the h itself should be negative. That means they exclude everything where the h is positive. So here you should be. They also say that the mu should be positive. That means they exclude all these points. So the remaining quadrant is this one. But then they also say the product of the two should be 0, which excludes nearly all points apart from those on the axis, which is this and this. So it's a strange set. We call it L-shaped. I mean, the other direction it would be an L. It is kinky, so it has a corner. And this is the set on which the combination of mu and h are allowed to live in the solution of an optimization problem. And a lot of the difficulties in optimization are actually due to the fact that this set is not a differentiable set. So it has a corner point. And this is the point where we usually, so to say, have problems. And sometimes we want to exclude that point. So maybe I should make it, and I want to give a few definitions. And the definitions are, so we regard a KKT point. I call it a KKT triple, which consists of a primal variable and a lambda and a mu. And so they satisfy the KKT conditions and LICQ. So that's what I just assumed. So I have such a point. And now I could look at the multipliers, and I know that they will be, this combination of mu and h will be on this set. And so now I can either say a constraint is inactive. So if I'm here in this area, I say, that's clear, constraint hi is inactive. That's what we had already before, right? And so maybe I use a green to define what I mean. So this is the green set. It's excluding the point, because at this point it will be active. So then I have, now I have too many colors, right? So I don't have enough colors, sorry, I only have 3, I think, that's bad. So if I'm here, but not at this point, then I say, maybe I put it here, it's strictly active. I mean, it's active, but it's strictly active because it's also positive, the multiplier is positive. And at this point, I call the constraint is weakly active. Yeah? So maybe constraint is inactive means hi of w star is smaller than 0. Weakly active means it is actually equal to 0, and the multiplier is also equal to 0. And here, strictly active means the constraint is, of course, 0, but the multiplier is positive, strictly positive. So these are the 3 cases. Inactive we know, and among the active ones we can still distinguish between strictly active and weakly active. So these are definitions I wanted to make. And then there is some definition that sometimes is useful to make, and it's an assumption. 317. And so at such a point we say that strict complementarity holds if there is nothing that's weakly active. So we are either here or there. at W star, lambda star, mu star, strict complementarity holds if and only if no constraint, no inequality constraint is strictly active, is weakly active. Yeah. So that is the easiest case to treat usually, because once you're at this point, you get this non-differentiable nature, and it's slightly more complicated. So I mentioned here, I didn't say KKT plus LICQ, so they should hold both. But then we say strict complementarity holds if and only if no inequality constraint is weakly active. Okay. What I wanted to say in a few plots is this graphical interpretation of the KKT conditions. It's 3.2.1. And I want to stay in this picture of the fence and the landscape. And in this landscape, we could have an objective function, and typically we illustrate things also on maps by level sets. Here would be the deepest point of the valley is at the bottom, and then we could have a fence. But we could also have an equality constraint, and let me start with an equality constraint because it's a slightly easier concept. If you have an equality constraint, then it means that on this landscape, you're just allowed to move on a rail. So it's not a ball anymore, it's actually a train that goes across your terrain. So it's a rail, so to say, and you're just allowed to move on this rail. And so there will be a minimum point on this rail, and this minimum point will be here. And you see that's the minimum point on the rail. And that will be the point where the gravity force will not pull you into the direction of the rail. And so the gravity is, these are level sets, they are the gradients of f. So the gradient of f is orthogonal to these level sets. So the negative gradient is actually pointing in the direction which goes down. So that's negative f. Yeah? And this, if this could be your point w star, for which we want to check optimality, then we know that because the force should push not in the direction of the rail, it should be in the same direction which is collinear with the which is orthogonal to the rail, which is actually the levels is the gradient of g. So this is the set where g of w is equal to 0. And so we basically say this should be equal to the gradient of g at w star times some multiplier, because the force, the strength of the force is something that could be arbitrary, but it should be definitely in the other direction, and together these forces should add to 0. So that's a little bit of intuition behind these KKT conditions. Maybe some interesting thing is what happens if I would move this rail. This is a bit funny, I could move the rail, right? But now I look at a different situation where my rail just goes through the minimum of my optimization problem. What would happen there? At this point, I wouldn't need the rail anymore. I would be anyway at this point. So at that point, actually, my multiplier lambda will become 0. For an inequality constraint, it will not matter, but for an inequality, it would matter. Actually, for an equality, it will not matter. If I move my constraint further, so I could move over here. Now I have a rail. Okay, so the rail will still constrain me to be on this line. So I will still be at this point. But now my force will have changed. The gradient is now pushing into this direction. Also my constraint function must push into the other direction. So at this point where I cross, so to say, the minimum, my multiplier will have changed sign. For an inequality, this is not a problem. For an equality, this is not a problem, right? It will actually remain similar. But for an inequality, if this would have been a fence, yeah, so you have your fence, you have your ball, and then you move your fence, and when you're moving up the hill again with your fence, your ball will not follow you, it will just stay at the bottom, right? So at that point, you will see that the multipliers cannot change sign for a fence. So what would be a fence in the same picture? So here are the level sets, and your fence will forbid to be on that side. So your minimum will somehow be here. There will be a positive force in the direction of the constraint gradient. So this is the set where h of w is smaller than 0, and this is the set where h of w is bigger than 0. And here on this fence, w is equal to 0. Everything here is allowed, everything here is forbidden. And so now the gradient of w should point, because it's getting smaller here, so the gradient will point actually in this direction, right? So it's something that points into this direction. So it will always point upwards where the function h grows, right? So this is gradient of h at this point. And the condition that we just had before is that the condition, the downwards force, this force should be equal to the gradient of h times w star times mu star. So here you see already if they should be equal, the mu must be positive in that direction. Maybe it would be, and another way is to just put this to the other side and say all forces should add to 0. Okay, and so what I wanted to illustrate is if I now move to the point where this fence goes through the deepest point of the valley, at that point I don't need a constraint force anymore. My multiplier would go to 0, and if I would move further up, the multiplier would have to change sign, but at that moment it will become not a minimum anymore, because the fence, as I said, it should not hold the ball, right? I mean, the ball will stay below. So I hope that gives a bit of intuition on why these complementarity conditions should hold. So you see that something non-differentiable happens if I would move my fence over here. I mean, the minimum will travel to this point, and when I move further, it will stop traveling up. I mean, it's something I could easily visualize if I had a ball. Yeah.
Short question. So
yes.
If I have a second quality constraint that is,
yes.
let's say, orthogonal to the rails,
yes.
Is this case this one where I have a point where the...
No, it's unrelated. So this is a diagram mu and h.
Yes,
so
sure, is at this point the two vectors, like the gradient isn't
maybe I should
orthogonal and...
So maybe I should just say a few words. So if you have, you just said, let's visualize the case where you have two rails, right? One rail here and maybe another rail here. And you want to be on both rails. That's, of course, not so easy to visualize, right? I mean, there is no train anymore that can travel. It can just be a point that is here. And, of course, there is no optimization to be performed anymore because that's the only feasible point. But anyway, you can formulate KKT conditions, and it turns out that your two constraint gradients, I mean, they are in this direction and in this direction, together they span already the whole space. And so they can reproduce, so to say, any objective gradient, and you can always find lambdas that will make it happen. And the same holds, by the way, also for inequalities, but there they should be positive, and that means that your corner can only be a corner where this corner would be a... Now I make these two things becoming inequalities now, just to make it a bit different, right? Then my allowed set is here. And now, okay, it's depending on how I visualize it. In this context, I think the minimum point would be here in my drawing, and not here. And you can easily see, so to say, that this is not a KKT point because the gradient of the of the objective would pull you at this point in that direction, slightly away from this constraint. And so this multiplier could not help you to pull it into that direction. So it will actually continue to move a bit until it's here, and here the equilibrium is between that force and that force. Yeah. So I think if I want to really, so that's the gravity force, and that is